Hello, everyone. For the two of you joining early, as usual, we'll start in like 6 minutes.
Good morning.
Morning. Um, Okay. Hey, good morning, students. How's it going? Thumbs up. Well, yeah. So today we're just gonna do more stuff with lenses. The chapter is kind of split into halves. I mean, the real math happens when you talk about the mirrors and lenses, but then there's a whole bunch of conceptual stuff on how the eye and the camera works. But biggest takeaway from the chapter, in my opinion, is just understanding what happens when you have mirrors and lenses put together and how you can measure the magnification of an object using the locations of the actual object in the image, as well as the angular size for telescopes and microscopes. So everything that has a formula tied to it is the most important takeaway. Yeah, before I forget, there is the second lab coming up on the 26th. I'll get the lab outline a couple of days before that, so you can prepare. It's not much to prepare for, just kind of setting it up before the lab starts. And other than that, the third assignment, I think, would become available either probably next week. We'll have a while to do it anyway, since the third assignment is meant to cover all the light chapters. So it's going to cover some stuff we haven't seen yet, which is diffraction and polarization. Anyways, for today, we're just going to do more lens stuff since we talked about mirrors last time. Let me just hop onto that. Okay. All right. Lenses are geometric shapes that refract light. They overall tend to converge light rays or tend to diverge them. So they kind of change how objects look, and that helps correct your vision. It helps you see faraway planets with a telescope, or that lets you see things that are close to you but really tiny with a microscope. The actual geometry of the lens is a two-sided refracted surface, right? It's like a prism, and to figure out how an image is formed across a real lens, you really have to consider both surfaces separately and kind of join them together. But under the assumption that the thickness of the lens is much thinner than the curvature of the surfaces, you can treat the lens as a single refracting unit, as a thin lens. And that tends to simplify things so that you can talk about the image and the object with one formula. That said, though, the focal length of a lens is a property of the lens itself. It's a property of the material it's made of and the roundness of its sides. So the formula that relates the focal length of a lens, and again, the focal length is where the focal point is. So every mirror, every lens has a focal point, which is where part of the light rays converge. So it's more or less the area where the reflecting or refracting object likes to bring light to. So there's this formula, the Lensmaker's equation, that tells you what the focal length is going to be based on the index of refraction and the geometry of the lens in question. So two types of lenses, here we show them. There's the converging lens in figure A, which has a convex shape. And in figure B, we have a diverging lens, which actually has a concave shape. Note that, right, one has a real focal point, since light beams actually converge, while the divergent one has a virtual focal point. So that's a formula for figuring out where the image gets made, which is the same formula for mirrors. And that's why sometimes we call this the lens and mirror formula. But if you know the focal length and where the object is located, you can figure out where the image is going to be. And you can also figure out where the image is going to be by drawing the beams coming out of the object towards the lens. So with these drawings, you need to just have a good ruler handy and really have a scale set up so you can write exactly where the object is in relation to the focal points. And then from there, you go ahead and draw. All you need is 3 rays. You actually need 2, but a third one's a good way to check. And you're gonna draw 3 rays, and wherever they intersect or appear to intersect, that's where you're gonna draw the image. So the 3 drawings show essentially the 3 possible images that can be formed with lenses. The converging lens shown in figure A and B can create 2 kinds of images. If the object is far away from the focal point, like in figure A, you create a real image across the lens, and every real image is upside down. So a virtual image across the lens, virtual images are upside down. If the object is within the focal length, so it's between f1 and the lens, like in figure B, the image is real and it actually shows up on the same side as the object behind it. C shows you the ray diagram for a diverging lens. No matter where you place the object, anywhere, whether it's on the left side of f1 or on the right side of f1, it always creates a refracted image that's on the same side. So it's always going to be a real image, and it's always minified. So these diverging glasses tend to make a smaller image. So rather than having, if you took a magnifying glass which uses a diverging lens and you swapped it for a magnifying glasses use converging lenses. Now suppose you have a glass that's a diverging lens. What you end up with then is a minifying glass. They will make the things you see through the glass smaller. And compare that to the converging lens. When the object is close to the lens inside the focal length, they create an image that's bigger. So that's how magnifying glasses work. If you have 2 lenses put together, what you can do is you can use the lens equation. You can treat them separately, and then you just check out what image is formed through lens 1, and that image that's formed is going to be what passes through lens 2. So the image of lens 1 becomes the object for lens 2. You can use the lens equation 1 lens at a time. Same with mirrors. You're just gonna break it down into steps, and you don't worry about the other ones until you get to there. The only thing worth pointing out though is that every time you pass through a lens and a mirror, there's magnification happening. So the image through lens 1 gets magnified and then it gets magnified again by the second lens. So the total magnification is a product of all the magnifications that occur on the way. If you have 2 lenses stuck together, the lens formula is a bit complicated, but it can be simplified to just the sum of the inverse focal lengths. And this is actually the same as having a single mirror that has a focal length, which is the sum of the reciprocals of the individual ones. This is, if you take an E&M, this is kind of like an equivalent resistor when the resistors are in parallel. When you put 2 lenses together, their equivalent focal length is smaller than either one. So if you have 2 mirrors, 2 lenses put together, and their focal length, each one is 10 centimeters, when you put them together, that's the same as having a single lens of 5 centimeters. In other words, putting lenses together gives you a shorter focal length. To give you an idea of what that physically means, if the shorter the focal length of a lens, the sharper the angle that light's going to make. So If the focal length is really close to the lens, it means it's really small. The rays are going to get severely drawn in or drawn out, depending on the type of lens. In other words, a glass with a really long focal length means that the distance to the mirror, to the lens from the focal point is really long, really far, so the rays don't really diverge or converge as much. So farsightedness is where you can't see objects near you. Normally, you can't see most things around you up to like 2.5 centimeters, so that's really close to your face. If you are farsighted, though, the limit is more than that. It's, you know, could be like a meter away or so. So everything a meter to you or closer looks blurry. So what glasses do to correct that is they are made of converging lenses so that everything close to you now appears farther away from you so you can actually see it. It creates images outside your range of blurriness. So if you can't see things within a meter, your correcting glasses are going to make images that are at least a meter away from you so that you can see them. If you're nearsighted like me, you have the opposite problem where basically, if you have a healthy, perfect human eye, 20/20 vision, the farthest you can see is as far as you can, really. Your eye can focus into the sky, to anything, really. If you are nearsighted, though, your eye can only focus so far. In my case, my eye can focus, I don't know, I want to say like 15 inches in front of me. Anything past a 15-inch radius is blurry. So what my glasses do is they take everything and create images that are within that 15-inch radius. That's called the far point, by the way, which is the farthest thing your eye can focus on. If you've got healthy eyes, the far point is up to the sky. It's like theoretically infinitely far away. You can focus on everything that's far away from you. In my case, it's 15 inches. So as you can kind of see in the drawing here, the glasses that correct for nearsightedness create images at the far point. They bring the image closer to you so you can actually focus on it. And if you wear contacts or glasses, you may have seen your prescription has like +5, -2, -3 or whatever. That's actually the measure of the lens's power, and that's actually 1 over the focal length. The reason why that is because the shorter the focal length, the more the glasses converge or diverge light. So power means that it's converging or diverging at a much sharper angle. If the focal length is really big, it's a smaller angle, so the glasses are not as curved. In other words, if your glasses have very low power, that means that the focal point is really far away. So your glasses look almost kind of flat. But if your glasses are very curvy, that means that they have a very short focal length, and so they have much stronger power. Basically, the worse your vision is, the curvier your glasses, which is why my glasses are super curvy. Anyways, magnifying glasses, the way they work is the healthy eye can really see images up to like 25 meters in front of you. Like you can focus on things 25 centimeters in front of your face. Anything close from that is blurry. So what a magnifying glass does is it's gonna take whatever you're looking at and make it look bigger. And the biggest it can be is if you're looking at it 25 centimeters from your face at the near point of your eye, because the closer you bring something towards your face, the bigger it is. So to maximize that, you want the image to be made at that near point. So overall, then the eyepiece here, the magnifying glass, at the very least, it can magnify things by the formula shown here which is the near point of the normal healthy eye divided by the focal length of the glass. So the more powerful the glass, the shorter the focal length and more magnification. And then at most, it can magnify things according to the formula here, which is just 1 plus the minimum magnification. And for the record, these are magnifying glasses are converging glasses. So they are convex, and only when you bring something really close will you get it magnified. So this is a virtual image. If you pull the magnifying glass away from that, and you just kind of glance around with it, you'll see that everything looks inverted. Because when things are far away from a magnifying glass, everything's upside down because it's creating real images. It's only when you bring something close to the magnifying glass that you see the virtual image, which is upright and magnified, like in the picture here. Anyways, microscopes, like you did in biology class, they let you see small things in a much bigger scale. So they use two glasses, an objective one that can be adjusted and an eyepiece that can also be adjusted. But overall, the object you're looking at is actually really close to your eye. It's just tiny. So it creates an image that's really far away so as to maximize its magnification. And you can then figure out how much bigger the image is going to be depending on the length of the microscope and the focal lengths of your objective and your eyepiece. So the more expensive microscopes then have really, really good lenses with really small focal lengths so that the magnification is even bigger. But again, it's not cheap. If you're working with a regular telescope, telescopes, unlike microscopes. So microscopes, there's a tiny thing close to you. You want to see it bigger. Telescopes is about looking at the sky. Things that are really far away from you and really tiny, and you want to see them bigger. So the object is now really far away from you. So the construction's a little bit different because the object's so far, but the most basic telescope is still the same idea of using an objective lens and an eyepiece lens. And when you combine them, you can create an image that's magnified. And magnification, in this case, is just the ratio of the focal length of the objective lens divided by the focal length of the eyepiece lens. It's also worth pointing out that telescopes can be made with mirrors. Anyhow, so here's a question for all of you to try. An object's located in front of a converging lens. It's 8 centimeters from the lens, and the lens has a focal length of 10 centimeters. And my question is, what is the image? So you can do this both ways. You can use the lens equation, and you can also use the ray diagrams, right? Which really, both of them should be there to be a double check on each other. The lens equation, right, tells you exactly where the image is if you know the object and the focal length. But we should be able to do a lens diagram as well. So, if we had to draw a lens diagram, you have a lens here, and let me draw like an axis through it, a central axis. And you know that the focal length is 10 centimeters, so here's one focal length, and here's another focal length. But we're told that the object is 8 centimeters. So it's actually inside. The object is inside the space between the focal length and the lens. The object's over here. Yeah, so maybe take a few minutes to figure out the image. So it's worth pointing out that for a converging lens, the focal length is always written as positive. So we go ahead and figure out what the Q is. We'd get F times P divided by P minus F. I'm just doing a little bit of algebra. All of that, both F and P are positive in this case, right? So you got 80 centimeters divided by 8 minus 10. And Q is equal to 80 divided by 2 centimeters. Q is equal to negative 40 centimeters. Okay. So, so according to the lens formula, the image formed when the light of the object refracts through the lens is negative 40 centimeters. So based on that result, is the image formed on the left side of the lens or on the right side of the lens? What do we think? Anyone?
Right side.
So in this case, this is when we have a situation here. Yeah, the object is really close to the converging lens. And when that happens, what it actually creates is a image on the same side as the object. So when Q is negative, it means that it's on the same side as the object. It's not, when we're looking at mirrors, it was the other way around. But in this case, a positive value of Q would mean that it will be on the right side. If the value is negative, it's on the same side as the object. So we got a negative number for Q. It's positive. So Q is on the left side. The image is being formed. It appears to be formed on the left side. let me show you a ray diagram. So let's draw some rays. One ray always goes right through the center of the lens, goes straight through. And another ray goes through the first focal point. But we actually can't go through the first focal point because we're in front of it. So the ray doesn't actually go through the, I need to make this a bit bigger. So there's a ray that goes through F1, but in this case, because you're in front of it, you don't actually go, the light ray doesn't actually go through it, it just appears to go through it. So kind of have it go like this. And you kind of see how it appears to be coming from F1, even though it's actually not. And then this ray goes parallel. And then there's a third ray that will start off parallel and then go through F2. So these rays, where they converge, that's where the image is formed. But they're not actually converging. They're not on the right side of the lens. They're all spreading out, going on their own way. They're not going to meet, but they do appear to meet behind the lens. If you look at the refracted ray, here's one, and you kind of draw their path behind the lens. Yeah, got in white. So just gonna. So they appear to be coming on from the left side of the lens, right? And if you trace that back, the lines do meet on the virtual side. And they meet, I guess I'm turning at this slide. They meet like over here. And where they meet is where the image is located. So based on this ray diagram, we see that the image is on the same side of the object, which is exactly what the math told us, and negative 40 centimeters. So that's farther to the left than even the object and the focal point. So that's what the ray diagram agrees with. And it's magnified. It's larger than the object. And if we do the math for magnification, right, we get m is equal to negative q over p. That's equal to the object distance, image distance negative 40. The image distance is negative 40. The object distance is 8. So the magnification is 40 divided by 8. Negative makes it positive. It's 5. The image is 5 times taller than the object, which the ray diagram agrees with. So it's also worth pointing out that being a virtual image, it's always going to be upright. So does this ray diagram make sense? Does anyone have any questions about ray diagrams? Okay, you're probably going to have to do one for your for the assignment coming up. So just with a ruler, it's usually not too much of a hassle. Okay, so for timekeeping purposes, this question is just asking, you have an image passing through a lens, but now you cover half the lens. And what happens to the image is the question. So I'm just going to go ahead and discuss the answer here. If you think about it, the light beams kind of come from the object in all directions. So if you block half the image still gets to form, right? Because light beams are coming from everywhere. So just by blocking the image, it'll just mean that some light beams don't go through, but some still do, right? Some in the top part still get to pass through and form the image, just not as many light rays as before. So the image is formed with less light than it should, but it's still formed. So the image is still there where it should be, it's just a little bit faded. So the answer will be number 2. Okay. So next question. You're looking at a swimming pool, it's 1 meter deep. And the question is, how deep does the pool appear to be? Basically, because the pool and the air act as, like I said, refracting surface, if you're like standing above the pool, everything inside the pool looks shrunk. So the images created by light coming out of the pool are minified. And the reason that is because the pool has a higher index of refraction than the air above it, which makes all images virtual and smaller. So you can kind of see that in the drawing here, how you have this fish at the bottom of the pool, and light coming out of the fish, once it reaches the air, kind of fans out. And that means that what you actually see, the image of the fish, appears to be a lot closer to the pool, sorry, to the surface. So everything appears closer to the surface than it actually is, right? If you've ever gone swimming, things look like they're close to you underwater, but then you actually go underwater and they're farther than you thought. So how deep does the pool appear to be if it's 1 meter deep? Well, in this case, you have a refracting surface that's flat, right? So for a flat refracting surface, the formula here, the refracting formula for flat surfaces, right? You've seen this in the slides. The radius of curvature of the surface is essentially infinite. So you can find then the location of any image by knowing the indices of refraction and the location of the object. In this case, the object is just the bottom of the pool. So we would have the answer would be, but just solving for the position, you'd get the, where'd I go? For solving the position of the item, of the image, I guess, I keep saying item, you'd get P times N2 divided by N1. And there would be a negative sign here, actually. Note the negative sign, since the object is usually real, this ensures that the image is always a virtual image, so it's always on the same side, it's always in the water. And then we know that the object is 1 meter in, so times N2, that's the index of air, divided by that of water, which is 1.33. So the location of the bottom of the water, the bottom of the pool, seen from above, is 3/4 of a meter. In other words, the pool looks like it's only 3/4 as deep as it actually is. Anyway, so in this question, you're told the index of a plane convex lens. You're told one surface is flat and the other has a radius. What's the focal length of the lens? So for this, you can always use the lens maker equation. Which again tells you what the focal length is in terms of the properties of the glass. So I'm just writing it out here, 1/R1 minus 1/R2. So when you're told you have a flat surface, that's essentially the same as having an infinite radius. So one of the terms goes away. And that leaves you then with the formula simplifying a little bit, n minus 1 divided by 1/-1/R2. And in this case, we do know the index of the glass, we do know the radius. So if you plug it in, you end up with a focal length of 40 centimeters, which in this case, actually there should be, because there's a negative sign, you should end up with a focal length of negative 40 centimeters. That just means that the focal length is actually on the same side. A negative focal length means that it's that the focal point is on the same side as the object. So it will be on the left side of the lens, not the right side. Okay. An object is placed 6 centimeters in front of a lens that has a focal length of 4 centimeters. Where's the image located? What's the magnification? So right off the bat, you're told where the object is, you're told what the focal length is. A positive focal length tells you that the lens is a converging lens. So knowing that it's positive focal length, that means focal length rays actually will pass through and converge across the lens. So you know it's a converging lens. So we know it has kind of like a teardrop shape. And converging lenses can form real and virtual images depending on where the object is. In this case, the object is farther away from the lens than the focal point. So the focal point is over here. And if the object was between the pink mark and the lens, it would create a virtual upright image. But in this case, the object is 6 centimeters. So the object is actually somewhere like over here. And when the object is far away from when it's behind the focal point here, it's going to create an image across the lens. It's going to create a real upside down image. As a matter of fact, we can do a ray diagram to show that off. So let's draw the object. Here's the object, and let me draw. We're going to need to draw the focal point on the other side of the image as well. On the other side of the lens, I mean, and make sure that this actually like equal distance. Okay, and this is let me label some stuff. Here's the object point. Here is the focal point number 1, and here's focal point number 2. So let's do a ray diagram. So we need one ray that goes through the lens. Let me show you this pink. So one ray goes right through the center of the lens, straight through. Another ray goes parallel and then refracts into the second focal point. And the last ray goes through the first focal point and then refracts parallel. So once again, I made the lens a bit shorter than it should be. There we go. And well, adjust that a little bit. There we go. Okay. So then this is going to refract parallel. This. And where the lines meet is the point where the image is located. So somewhere around here, the image is made, and you can see then that the image is in fact upside down. And it's actually magnified. So I didn't even have to use the lens formula. Hey, I just kind of plugged everything in. So that's a cool thing with the ray diagrams, to give you an idea of what the answer should look like before you even do any math. There we go. If you go ahead and do the math, what you should get then is a object distance, right? If you use the lens formula, what you end up with is a lens distance that's equal to, an image distance that's equal to 12 centimeters. And it's positive. 12 centimeters positive means that it's on the other side of the lens, it's on the other side of the object. And if you do the magnification formula, you get negative 12 over 6, and that gives you a magnification negative 2. So it tells you that the object is upside down and twice the height. Also went ahead and took a drawing from an applet, which I sent to you in the last tutorial. So you can always use the applet to have an idea what the ray diagram should look like. And this is exactly the situation that's happening in this example. Okay, so this is where it gets interesting. Now we have two lenses. And the image that's formed across the second lens has already been sort of warped by the first, and we want to find the position of the final image. So what we're going to do is, for this type of problem, you want to start off with the object here, look at the image created by the first lens, and now you're just going to forget about the first lens and only look at the second lens. So the image created by the first lens is going to become the object for the second lens. And then you got to be careful, right? Because when you calculate the image distance from the lens formula is going to be relative to the first lens. But once you treat that as the object for the second lens, you have to treat the distance, you have to recalculate your distance relative to the second lens. So the image distance is measured from here to here, but the object distance is measured from here to here. Anyways, once you know that, then you can just use the lens formula again. You can now forget about the whole first lens thing and get the image distance for the second lens, which is the final distance. So again, one step at a time, let's do the first lens first. We know where the object is. It's 60 centimeters from the first lens. We know the focal length of the first lens, so we can just find the first image that's created. The first image that created has a location of 12 centimeters. So if you rearrange the lens formula, you get that the location of the first image is equal to the location of the object times the first focal length divided by the position of the object minus the first focal length. I'll give you a 1. So you get a image distance of 12 centimeters. That fact that it's positive tells you that it's being made on the right side of the lens across the object. And to use that image is now going to pass through the second lens. So it's going to be the object for the second lens. And that's a distance measured from image 1 to the second lens. So it's 12 centimeters on the other side of the first lens. And you know that the distance between the two lenses is 40 centimeters, which means that the distance between the image and the second lens is 28 centimeters. So we know that this distance is 12, this distance is 40, so the distance here must be 28. So that's where the object is located. And now then we're just going to see where this ends up when you pass it through the second lens. So you're going to do the lens formula again. And that gives you, what you should get is a volume of 32 centimeters. So it's a similar formula to the one you just did. you should end up with, let me just put it down here. The fact that it's 32 centimeters positive, it tells you it's made on the other side of the second lens. Okay. So does anyone have any questions about this? Does this make sense? Okay. We'll do one more of this. So this one's trickier. It's a similar idea where you have two lenses. You know the location of the object and two lenses. And then you want to find the magnification of the object in the setup. So when you pass through two lenses, the total magnification is magnification to the first lens times magnification to the second lens. This is a weird case though, because when you pass through the second lens, the image actually forms in front across the second lens. So the image is not formed between them, it's formed on the right side of the second lens now. We don't even have to do a ray diagram. We do the math. If we calculate the image being formed across the first lens, right, we're going to use the lens formula with the object distance and the focal length of the first lens. We get that the image is formed 100 centimeters to the right of the first lens. The distance between the two lenses, here is 60 centimeters, right? There's a little bit of a problem and there's a distance between them. But the image is 100 centimeters. So the image is actually being formed, right, like all the way past the second lens over here. So that means then that when you look at the refraction for the second lens, the object is on the right side of the lens. So that means that the object is on the virtual side, which means that the object for the second lens is now going to be, it's going to be a negative sign to indicate it's on the right side of the lens. Because the object is, because the image is created at 100 centimeters on the right side of the first lens, and there's a distance of 60 centimeters, the object location for the second refraction is going to be negative 40. So following that, now that you know where the second object is,
Sure.
you can calculate the image being made.
Sure.
Yep.
How do you get P2 equal to negative 40 again?
So we figured out that Q1, the image formed across the first lens, is 100 centimeters. It's 1 meter to the right of the first lens. So where am I? So I had to draw Q1. There we go. Q1 is 100 centimeters. Now, where this image forms, this image actually acts as the object for the second lens. But the object distance is measured from the lens in question. So the second lens, the distance between the second lens and this image is not 100 centimeters. The distance between the second lens and this image is the distance from the second lens to where the image is being formed. So this distance right here, because you know that the lenses are 60 centimeters away from each other, then this distance here must be 40 centimeters.
Okay. Okay. Thank you.
Yeah, so, and then another thing to consider though is the fact that because we're on the right side of the lens, we're across the lens, the object then will be measured with a negative sign. The object distance will now be a negative 40 centimeters to indicate the fact that we're across the second lens. So because like objects like the one that we start off with, the one on the left side, we start off with a positive object distance because we're on the left side of the first lens. When we look at the second lens, the object starts off on the right side, so we use a negative sign for the object distance. So we go ahead then and calculate where the second and final image is formed. Again, similar formula where we have F2 times P2 divided by P2 minus F2. And what that gets us is about 15.38 centimeters. And again, a positive value for Q2 tells us that it's going to be on the right side of the lens. So it's actually, in this case, it's actually on the same side as the first image. So it's 15.38 centimeters to the right of the second lens. And that's going to be a real image because it's on the other side of the lens, it's on the right side. And it's actually going to be upside down despite being a real image. The reason why it's upside down is because when it passes through the first lens, it gets flipped. The light beams get flipped upside down. You can figure this out though, because we're looking for the magnification. You need to calculate the magnification separately and then multiply them together. So the magnification of the first lens is the image distance 100 times divided by the object distance being 25. So you would get about negative 4 for that. And the second magnification would be the object being made 115 centimeters. Sorry, the image distance is 15 centimeters from the second lens, and the object distance is 40 centimeters on the right side of the lens. So the second magnification is negative 15 over negative 40. So if you multiply those two magnifications together, the total magnification becomes 1.15. The fact that it's positive tells you that the image ends up being upright. And the reason why it ends up being upright is because of the two lenses. So normally a real image like this one, if there's a single lens making a real image, the real image ends up being upside down, but because of the two lens setup, you end up with a real image that's actually the right side up. But actually, no, sorry, my bad. the image is, I forgot a negative sign. The image is actually upside down. So a real image is upside down. So there's actually a missing negative sign in the equation here. This should be, it should be negative 1.5. So, sorry, because the image, yeah, the image does get flipped. The image gets flipped once by the first lens. The second lens does not flip the image, so the image remains flipped, which means that the final image is still flipped, it's upside down, and its magnification is 1.5. So the image that gets made is still taller than the object, just upside down. So yeah, you have to be careful with the sign conventions. As you can see, I'm still don't get them quite right from time to time. So basically, the way to remember it is that with lenses, you want things to cross the lens. So images across the lens, converging across the lens, where you want them to be at a positive distance, but on the same side as the object or negative. Well, with mirrors, you want things to reflect. So images behind the mirror have a negative distance value, but images formed in front of the mirror have a positive value. So it's kind of like it's the other way with lenses, where if the image converges on the other side, it's positive, but with a mirror, it would be negative if it appears to reflect off and converge on behind the mirror. This takes some practicing, but as long as you can draw the ray diagrams for your lens and mirror problems, you can figure out where the image should end up with. So whatever sign confusion there may be, if you just take your time and draw the geometry, you can get it right. And there's always the tables in the textbook. I think we have some of the slides too that talk about the here. Okay. Yeah, there's some tables though that tell you what the sign should be for each case. And there's a summary here on the slides that tell you what kind of image gets formed no matter what. So just kind of doing a few practice problems and getting the hang of it. What was I gonna say? Yeah, we're out of time. There's a few more problems in this slide. I put up the solutions in the slide notes, so you can kind of look at that. If you have any more questions about them, of course, you can just email me, message me, talk about them more. But that's all the time we have to talk about this chapter in that tutorial. Next time, we're going to be talking about the chapter 37, which is talking about diffraction. That one's a shorter chapter, but it's kind of like a geometrics heavy one. So be sure to remember what you already learned about constructive and destructive interference, because it's going to make a comeback. And that'll take us through to the end of next week, where we'll do the second lab. And hey, I just realized that after next week, we have our spring break. Starting on March 28th, all the way through to April 4th, we get the week off. So that's exciting. Anyways, we're gonna get kicked out of the Zoom meeting in a minute anyways. I'm gonna call it a day now, so.
Thank you, sir. Bye.
Thank you. Bye. Have a good day.
Bye. Thank you.
No worries. Have a good day. Take care, everyone. Wish you all the best, and we'll see you Wednesday.